Hi, everyone. Today I'm gonna present this paper titled Understanding Contrastive Representation Learning through Geometric Hypersphere. In this paper, they introduced two new metrics for the contrastive learning. Let's see some background here. In many machine learning work, neural network based on machine learning networks, they try to learn the representation, and they usually use the L2 normalization, which will restrict the latent space to the unit hypersphere. And intuitively, we can see that if the representations are good enough, they can be linearly separable in the latent space. That's one big reason why in representation learning, we usually use the linear classifier to do the to predict the downstream task. Use this way to evaluate the quality of the representations. And besides the clustering property, we also want the representations should be invariant to unnecessary information. That's the famous Informix principle. We want to keep the mutual information between positive pairs as much as possible. And so how can we evaluate the quality of the representations? In this paper, the authors propose two metrics, alignment and uniformity, and they want to use them to interpret the success of existing contrastive laws, info NCE. And the left-hand side figure is show you the concept of alignment, which is a metric to measure the distance between the positive representations. For example, in the figure, the X, Y is a pair of positive samples. They are two augmented images from the same Y, and pass-through encoder F here in the latent space, their representations should be close enough. That's the goal of the contrastive learning. And another concept is uniformity. And this metric is to measure how well the representations are uniformly distributed, because later on I will give you this conclusion. The uniform distribution will preserve the maximum information. So that's another desirable property of good representations. We want to follow the Informix principle. And so here is some background and the introduction of the contrastive learning. Here we use the P data to denote the data distribution in n-dimensional space, and the P positive is represent the positive pair distribution over the Rn times Rn space. And here we use the encoder F, which maps the inputs into the d-dimensional latent space. And here is the influency loss. It's commonly used in contrastive learning. We have the denominator has the calculates the score between positive pairs, and the denominator includes the negative pairs scores. And so here is a toy example to show you to show you how we can evaluate and visualize those two metrics. In this experiment, we train the encoders in the CIFAR-10 data set, and we assign the dimension of the representation is 2, so we can expect a one sphere feature space, a two-dimensional space, and we're gonna compute this alignment based on the L2 distance of between the positive pairs. And we used here the Gaussian kernel density estimation to estimate the distribution of the representations. And then we visualize this. And here are 3 different training scheme. The first one is randomly initialization. We randomly initialize the encoder and fix the weights of it, and doing the contrastive learning. And here, all those results are for the validation set in the downstream task. That's a image classification task here. We can see in the random initialization, the uniformity is arc, and is just a very small part of a circle, and the accuracy is quite low here. It's only 71% accuracy. And as we used the supervised learning and contrastive learning, we can see the uniformity becomes more like a circle, especially for this contrastive learning. And also we have pretty low alignment. We can see the mean L2 distance is always less than 0.5. That's what we want. And yeah,
one question. So I think it's very intuitive to use like this sphere to show like the uniformity, or the to visualize the uniformity, right? But I maybe I have missed something you have already mentioned, but can you further clarify how can we generate this sphere?
You mean the circle here?
Yes. How can we generate this?
The basic idea is, first we will get the all the representations for the inputs, and we have a set of representations, and we use the Gaussian kernel density estimation, this method, to estimate the feature distribution on those two-dimension space. And about the details of the Gaussian kernel density estimation, I'm not quite sure about the details.
So the intuition here is this sphere can represent the distance between the features. Is that correct? So what's the intuition behind this sphere?
Yeah, they're related.
What's the exact, intuition behind this sphere? So, for example, you can see the leftmost figure shows like an arc, right?
Yeah.
And we have in the middle and in the right figures, there are a circle, and we have different color. What does that mean?
Here the circle here is overview of all the classes, and here I only show you the final results. Actually, in the paper, they give you several specific classes feature distribution. You can see that for each class, they have different position. For example, in the contrastive learning, this uniformity, it has a very perfect circle, but for like class 1, it only occupies a part of this circle. And let's say another class 5, it occupies another part. And so for this circle, they have they have distance that's related to the alignments, but in the position, they try to, for the class 1, other classes are all the negative samples, and we want to push them far away. So eventually we will have this trade-off. So in this paper, they give some theory proof and some experiments to tell you the uniform distribution will be the final balance when you have a good quality, good representations. So intuitively, if you have a perfect circle, it means all those classes are uniformly distributed, and they are far from the negative samples. So that's what we can tell.
Okay.
Yeah. Sorry about that. I should give you more examples here, because yeah, it make it more clear. All right, so here the conclusion here for this toy example, we want to say that the features from the contrast learning is most uniformly distributed. That's here we use the influency loss, and here is the result of the contrast learning. We can see that if we fully train the encoder, and eventually it will give you a circle-like distribution. So here is only for the 2-dimensional. So in high dimension, let's say n dimension, we will have n-1 sphere, and we also expect it's uniformly distributed for all the classes. And so here the author want to quantify those two concepts and use those two metrics to some kind of replace or interpret the influence loss. Here the alignment is intuitive. It uses expected distance between the positive pairs. When the distance equal to 0, it means those two positive samples are perfectly aligned. They have the same position in the latent space. And for the uniformity, to measure the uniformity, they use this logarithm of the expected pairwise Gaussian potential. Here, the x, y are independent sampled from the data distribution. And in this case, we assume, we regard those two x, y as the negative pairs. And the Gaussian potential is just a radial basis kernel function map the RD times RD space to the positive integer. And so we want to ask why we choose this RBF kernel to measure the uniformity. And here is an example. We use previous toy example, and we calculate the average pairwise potential of the various finite points collection. We have a set of representations we can calculate the pairwise the Gaussian function, and we will get the average G2 here, the alpha we set to 2, and so as we can see here, we have add another scenario. It's uniform distribution samples. That's ideally that's a ideal situation, and we can see the average G2, that's the uniformity measure, decreases as the distribution becomes more uniform. So it tells us this G2 is a good metric for the uniformity. This is only the empirical evaluation. Actually, in this paper, they give a mathematical proof of why the uniform distribution, the optimal, the optimal space for this uniform measure will be the space with the uniform distribution for this Gaussian, for this RBF kernel. And if you're interested, you can check the paper for the mathematical proof. Here is only the empirical evaluation. And so here they propose this theorem 1, which is to connect those two metrics with the info NCE. This says if we, as the negative samples goes to infinity, and the contrastive loss, the NCE loss, will eventually be as follows. And the right-hand side have two parts. The first term, if we have perfect alignment, it will give you the minimum for the first term. And for the second term, if the perfectly uniform encoders exist, they will form the exact minimizer of the second term. So with these two concepts, if you have a perfect alignment and you have perfect uniformity, it will give you the minimum of this loss. So it tells us that minimizing this influency loss indeed requires those two metrics. And so that's how they decompose this info NCE loss to two independent metrics. And here are some experiments. Since this is a contrastive learning task, it still follow the two-stage scheme. First, you have the training stage to pre-train the encoder with unlabeled data, and then you transfer the encoder to the downstream and train another classifier on top of the frozen encoder, and to predict or do some other downstream tasks. And here the encoders, they use different architectures based on the CNN or RNN. And for the downstream task, they use 4 different, the STL10, that's a image classification task. They use CNN, and NYU Deeps V2, that's a Deeps prediction task. They use CNN encoder, and ImageNet and Image 100, those 2 data sets, that's image classification, still use the CNN encoder. And the final one, the book corpse, that's NLP task, and they use the RNN. And the positive pair construction here, they use the very conventional measure for the image task, the two augmented images from the same image, and they use the neighboring sentence for the NLP. And they do the experiments with varying objectives. They train they pre-train the encoder with only the contrastive loss or the weighted combination of those three loss. And also they fine-tune a lot of hyperparameters like temperature, the batch size, and the representation dimensions. And here are some results. The STL10, that's a image classification task. And here, for each dot here, it has three-dimensional information. The x-axis is the uniform metric. The y-axis is the alignment metric, and the color denotes the accuracy for this classification task. And so we can see in this yellow rectangular, that's we have the high performance region. They give us the best validation accuracy. And we can see in this region, every dots have a very low uniformity and alignment. And also, we have here we have three different laws that used here. The dot here is only use one of the metrics, whether either the alignments or the uniformity, and the cross here only use the contrastive loss. That's the traditional contrastive learning, and the triangle here are some weighted combination of those three lost. So we can see almost in this yellow high performance region are from the, it's hard to say, but it's mostly come from the triangle. And so this is one, and here is another experiment, still this data sets. In this experiment, they changed the loss, the objective loss for the downstream fine-tuning stage. In the first graph, they fine-tune the whole model with only the alignment, and the second only with the uniformity, and the third with the both of those metrics. And we can see when we only use one of the metrics as the fine-tune epochs increase, this certain metrics will decrease, but another one will increase. So it will lead the validation accuracy somehow decrease. For the first two graphs tell you that. And the third one, you can see we can increase the validation accuracy by using both two metrics. So it tells us those two metrics are necessary for a good representation. And here are the conclusions and discussions. Actually, here I only show you two key experiments. Actually, in their paper, they give you more results to to give you a sense how to get the optimal, the optimal weights for each matrix, so you can get a better performance. And final, in their results, they can improve the accuracy based on their metrics than the info NCE lost, but the improvement is quite small. So basically, I think the key point or the insight of this paper is all about how to interpret the info NCE with those two independent metrics. And so here are the conclusions. The alignment and the uniformity are two important goals of the contrastive learning, and they can be good metrics to evaluate the quality of representation. And also this paper provides the theoretical proof that the uniform distribution on the sphere is the optimal solution for this RBF kernel. And but still, why this unit hypersphere benefits the representation learning remains unexplored. And that's all for my presentation. Thank you. Any question?
All right, so yeah, if there's no question, I guess we can conclude the seminar today. We'll see you folks again in